Okay, so good evening, everybody. I welcome you all to the third lecture of Professor Goswami. Now, from now on, these lectures will happen on a regular basis every Saturday and Tuesday. So, PNG, please go ahead.
Thank you very much, Rama. Thank you very much. And hello, everybody. Welcome to this third lecture. Today, I'm going to talk about atmospheric and oceanic waves. Basically, just before going forward, I would like to say that that we'll, just like the last lecture, we'll after half an hour, we'll break for about 15 minutes and take questions. And then again, towards the end, we'll take more questions. So that will it will give us some opportunity for interaction. So atmospheric waves, basically, the waves are essentially ubiquitous in atmosphere and the ocean. And there are different types of waves. There is high frequency, very small scale waves. Those are known as gravity waves, which are driven by buoyancy restoring force. On the other hand, there are large scale planetary waves, which are also have a lot of important implications in our climate and weather. And those waves have wavelengths much larger than the radius of the Earth, like of the order of the radius of the Earth, like 1,000 to 3,000 kilometers. And they are the main focus of this talk today. I mean, what I will try to do is show you what are the kind of waves that that are possible in the extratropics and in the tropics. So I want to keep this sort of differentiate between the waves in the tropics and extratropics, because this difference is sometimes very important. So the narrative will just sort of follow that guideline. So waves are, as I said, ubiquitous. For example, these are some waves in the atmosphere. You can see these are high frequency waves. These are gravity waves. They often produce very nice wave-like structures in the clouds. These are due to the updraft and downdraft associated with these waves. And if the conditions of the humidity and temperature are right, then they can produce these kind of waves. So this is another of such gravity type of waves. This was a picture taken in my region of the world over the Brahmaputra River. In this region, we have a lot of topography, and the winds interacting with the topography produces a lot of these gravity waves, and this kind of gravity wave structures are often seen when there is not too much of high convective activity, and these can be seen. When there are big systems, of course, you cannot see these waves. This is another one, similar one. These are also called Kelvin-Helmholtz instability. There are density differences in the two layers of the atmosphere, and these density, if there is a sharp density differences, this density difference can give rise to instability, and the instabilities can give rise to updraft and downdrafts. And those regions, again, if the humidity conditions are correct, you will get this kind of waves. And there are, of course, other waves in the upper atmosphere, which you can see through radars. These are the particularly pointing radars can give you the wind information from Doppler effect. And from this Doppler effect, the wind velocities at different layers can be estimated. And from their phases, you can see the phase propagation downward of many of these waves. These are that are filtered to retain the waves of periods about 8 hours or so. And these are filtered to fit the higher frequency waves to have between 8 minutes and 8 hours. So you can really understand through some of these various characteristics of these waves from such radar data. But today, of course, we have a lot of satellite data from which we can understand the waves also. This is another example of similar data from radar, which the vertical variation of this wave amplitude and then most of the characteristic features of these gravity waves is a sort of downward phase propagation. So in the other kind of waves are, of course, the waves on the very planetary scale waves. These, if you look at from the top of the sort of North Pole, for example, the geopotential height perturbations will show this kind of very large planetary scale waves. These are the waves I mentioned in the first two talks. These are the waves that produce extratropical weather. So this is now one picture is from looking from North Pole downward, and the other picture is from the South Pole downwards, from the southern hemisphere. And so in both hemispheres, you have this like, kind of large scale waves. So our main focus in this talk will be to understand these waves and characteristics of the wave, what produces them, also what are the kind of what are the group velocities, phase velocities, and what kind of spectrum they are allowed for these waves. There are also waves in the ocean. But this does not mean that those gravity waves are also very, very important. But in this particular talk, I won't have much time to really go into details of the gravity waves. The gravity waves are very important in actually producing, interacting with the upper atmosphere. They propagate upward, and then due to the mean density decreasing exponentially at higher up, the amplitude of the gravity waves becomes very large, and they break up. And they deliver energy into the mean motion, and therefore the mean winds at mesosphere and thermosphere are very much controlled by the gravity waves, which are generated at the troposphere. So they are very, very important, but unfortunately I may not have much time to deal with them very much, but I will talk about the larger scale waves in more detail. There are also waves in the ocean, and there are many types of waves we are familiar with, the surface waves, those are swells and other waves, but there are other larger scale waves also in the ocean. One of the examples here is an example from the Pacific, equatorial Pacific, where this is a picture of daily sea surface temperature from satellite microwave sensors give us satellite temperatures, surface temperatures, and on a very high resolution daily basis. And this is an animation of those surface temperatures for a particular period. And that the scale is the blue, and magenta is cool, the red is warm, and you can see that there is this between cold and warm waters. This surface has an instability which produces waves that propagate westward, and this is known as instability wave in the equatorial eastern Pacific. And this is another snapshot of that for one particular day. Based on this, actually you can calculate what is the phase speed. So you can do a sort of a cross section of this is at 2.5 degrees. If I plot the time and longitude plot, then you can see that these waves propagate, positive, negative phases propagate, and from these you can actually find out what is the wavelength. Wavelength of this wave, what is the period of these waves, and what is the phase speed, and so on. From the slope, you can find out the phase speed. So phase speed of these waves are about 35 centimeters per second, and their wavelength is about 1100 kilometers. So based on these, you can actually, you can then test with the theory what produces these waves and why. So now that we have a characteristic, scale of the waves and phase speed, the theory must explain those scale selection. And so in this talk, basically what I'm going to do is, but why do we actually want to understand these waves? Basically, understanding these waves are very important for actually for improving our prediction capability of weather and climate. And I'll just talk to, that towards the end of the talk. So in this talk, basically, I will introduce these Rossby waves, Kelvin waves, and mixed Rossby gravity waves, and the inertia gravity waves. And the gravity waves part, I have some notes at the end of the talk, but I will not be probably able to go through them. So what kind of waves are allowed in the atmosphere and the ocean? To answer that question, we have to answer basically start from the basic governing equations and basically linearize them around the mean, assuming that there is no mean flow. So we can linearize them, and from these linearized equations, you can look for wave solutions, and that is the standard way of looking at what kind of motions are allowed by the system. So for this purpose, what we'll do two sort of systems. One for the middle latitude beta plane, sort of channel in the middle latitude, and one channel in the equatorial region. And then I'll try to compare them, how it is the difference between the waves that are allowed in the middle latitude beta plane and those that are allowed in the equatorial beta plane, and what is the difference between them, and what is the difference in the dynamics of India. So this can be done essentially using a Cellular framework. Cellular, I don't want to go into philosophy of using this, but simply one can say that you can apply this kind of a framework for those waves whose horizontal wavelength are much larger than the vertical wavelength or vertical variations. So most of the planetary waves are like that, because therefore for the planetary waves, this is gives a zero order idea of the basic characteristics of these waves and their spectrum. And for that, so we assume a sort of channel somewhere in the middle latitude. Let us say this is F0 is somewhere around 40 degrees, let us say. And this has a channel of length L, and that particular the center of this is the Coriolis parameter is F. So with that, the perturbation of the free surface gives you variations in the height. So there is a mean height of this atmosphere. This is the depth of it can be in the ocean. It can be depth of the ocean. So or depth of the shallow water, whatever that is. That so this is kind of a scale height that we'll use in the atmosphere. Also, we can use a scale height for that. And that for that layer, we assume the the waves will produce the perturbation of the free surface, and the perturbation of the free surface will change the pressures and the pressure variations. Differences in the free surface variations will give rise to variations in the pressures, and the variations in the pressures will give rise to pressure gradient force, and that is going to drive winds. So these can be then then formulated using a very simple set of equations. So this is our momentum on the mid latitude beta plane. So we have this is the Coriolis force term, and this is pressure gradient term. Okay, so here the Coriolis we have used a beta plane approximation, assuming that it can be expanded linearly, and where this is the Coriolis parameter, which is the mean Coriolis parameter in the middle of that channel, and this beta 0 is the gradient of the Coriolis parameter, the variation. So del f del y is beta 0. So that is the gradient of the Coriolis parameter. Now the system has, and this is the sort of continuity equation. The system, the C0 square is nothing but Z into H0. H0 is the mean depth of the layer. So system has a velocity scale built in it. So, and there is a time scale associated with the Coriolis parameters. So there is a time scale and the velocity scale, and then we can use this time scale and the velocity scale to non-dimensionalize the variables, and so here there is some differences. In a way, you can take the Coriolis effect in a cell water equation. You can also take the Coriolis effect instead of putting this way. The oceanographers often use them as a gradient. If I have a bottom, if this the bottom is not fixed, but there is a slope, that slope will have a variation in the mean depth itself. Then variation of the mean depth can be shown to be equivalent to having Coriolis variation of the Coriolis parameter with y.
BNG?
So yes.
It will help if you tell like where equation 789 come from, and what is the phi over there.
Okay. Yes. Okay. So here, these equations are basically the momentum equations. So this is the u momentum equation and the v momentum equation. The x component of the wind, the y component of the wind. This is phi is what we call geopotential height. Geopotential height is defined here, z into h. So z into I showed you this perturbation so the pressure variations are associated with the variations in the depth. The depth is changing due to perturbation in the free surface, and this perturbation is associated with it. So this ZH is essentially proportional to the pressure, and therefore this is essentially a pressure gradient. And the Coriolis force comes from the formulation of the Coriolis force has a curl in it, curl of the wind, and that once you simplify and find the components of the equations, it can be written. The vertical component of the Coriolis force is this is here. So this is I have sort of left out the detailed derivation of this, but this is a kind of standard process which unfortunately I cannot go into great details, but these are the couple of things that is important. So this is this represents pressure, and it comes from the geopotential height, which essentially represents the density, the free surface variations. Free surface variations will give rise variations in the amount of water that is there, water or the fluid, and that will give rise to variations in the pressure. And okay. Okay. Having said that, so there is another way to produce the Coriolis effect, but here I will stick to the conventional way of that the meteorologists use, the use of the Earth's rotation or the Earth's vorticity. So with that, we can define a length scale, because we have a velocity scale and a time scale. And so once you have a length scale, time scale, and velocity scale, we can non-dimensionalize all the variables. And then the non-dimensional equations will then look like this. Now here again, this is the Coriolis term, and now we have these are all non-dimensional. Now we have a non-dimensional parameter here, which involves the mean Coriolis parameter, also the gradient here, and the length scale. And this turns out that for most of these large scale motions, these and in extratropics where middle latitude value of Coriolis parameter and their gradient and large scale of about 1,000 kilometers, this parameter is very small. So this is a smallness parameter in the system. So we can use that for some purpose of comparing, and I will come to that. So then we assume that, okay, what kind of wave solutions are possible? So we assume that, okay, let us have that waves that propagate in the x direction. And those such waves can be represented in the form of e to the power I kx minus sigma t. So sigma is, k is the wave number of the wave, and sigma is the frequency. So any wave can be defined in terms of a wave number and a frequency. And so then we can define a wave in this form, and then we we are allowing them to propagate in the east-west direction, but the structure of the waves will be constrained by the boundary conditions in the y direction. So those boundary conditions will allow only a certain type of waves that may be possible. Certain times may not be possible, and so that so we substitute these wave solutions in the basic equations, and then the amplitude of these waves. So U's are now the amplitudes of these U's are now functions of. So these essentially the waves are written as now all these U, V, and phi. These are the geopotential, the x component and the y component of the winds. They're all written as a amplitude which is a function of y, which is in the east north-south direction, and the propagating component of the waves in the east-west direction, which is given by these. So these, when you substitute in that, and then for non-trivial propagating solution, the amplitudes must satisfy these relations, and that from that we can actually solve how so why it is I sigma. This is so when you differentiate with respect to time, of course, it will give an I and sigma. And when you differentiate with respect to x, you will have a ik, and so on. But y we have not assumed anything, so y function will remain as it is. So therefore this part remains here. But all the others will have this coming out, and therefore we have a series of now ordinary differential equations with and then we can eliminate some and get an equation on the v amplitude, the amplitude of the meridional velocity. Why amplitude meridional velocity? Because we want to satisfy boundary condition, the no normal flow of boundary condition in the boundaries. So therefore we want to so I'd like to get an equation on V so that I can impose the boundary condition, satisfy this boundary condition on this V, solve for V. Once I have V, then I can go back and then substitute, and from other variables can be obtained from here. So you can eliminate and get an equation in terms of V. So this is finally our equation for the amplitude function, and that is simply second order ordinary differential equation, and this coefficients of the v velocity on these, it is something like a wave equation, but it is little bit complex. Here is a variation with y. So there is this coefficient is a function of y, but it turns out that in this is a smallness parameter because s is very small, and our y is this the channel is between plus minus 1, right? So therefore non-dimensionally, and therefore this term is always small compared to this, and therefore we can actually neglect this to the zero order. And therefore for the extratropical waves, the equation becomes simply a wave equation, very simple. This is the main difference between these, which I will come later on in the tropics, is that this equation for such the waves in the tropics will look like something like this, similar to that equation here, but there is no one, there will not be another one to compare with this y square term. And therefore, we cannot neglect this y square in the tropics. And therefore, it's a strongly dependent on y. This coefficient of V is a strong dependent of y. On the other hand, in the extratropics, it is a weak dependence on y. As a result, I can neglect this. And therefore, once we neglect that, then I can solve it very easily, because then, so now my equation is simply this. It's an ordinary wave equation, as long as this is a constant. This is, of course, for any particular wave, this is a constant. So therefore, I assume that that let us say that this coefficient is some alpha square. And that alpha square V will give me a wave solution in a sine and cosine term, right? So sine, so I can have a solution of this in terms of sine and cosine function, and I can find out these by using the boundary condition V is equal to 0 at y is equal to 0 and 1, and then I can find that A has to be 0, and only this term will give me the solution. And this means that sine alpha has to be 0, and sine alpha will be 0 only if these conditions are satisfied. Alpha square is equal to n square by pi square, or alpha square is nothing but this. So therefore, now I have a constraint for solutions which satisfying the boundary conditions require a constraint that these parameters are constrained by like this. So sigma square minus k square minus 1 minus ks by sigma is equal to n square pi square, where n can go from 0, 1 to 3, etc. This is what is now known as dispersion relation for the waves. So like that, I can always find the dispersion relation for these waves, whether it is for the extratropical beta plane or for the tropical beta plane. We can always find an expression. I'll repeat this in the extratropical beta plane. Now let us try to. This is what gives us what kind of waves are possible. The relation between a combination of wave number and the frequency defines a wave. So so now only a certain types of waves are possible, because this condition must be satisfied. Otherwise, it will not satisfy the boundary condition, so that wave will not be allowed. So this dispersion relation, let us look at this dispersion relation in some details to find out what kind of waves are actually allowed. So, and if you look at the high frequency limit, so when S, we already know that S is small, the sigma, if sigma high frequency limit means it is sigma is greater than 1. So that is like it is sort of periods are shorter than the rotational period of the Earth, so sort of shorter than a day. So those waves, we can neglect this term because this S is small and the sigma is greater than 1, and therefore this term may be neglected. And so what you get is a dispersion relation which is given by the sigma square is equal to 1 plus k square plus n square pi square, and therefore it represents a pair of waves. Now waves have, if sigma by k is positive, that means a wave is eastward propagating, that their propagation speed is eastward, positive is eastward, and if it is negative, it is westward. So therefore, this, if I define, this represents a pair of waves of same frequency and wave number, one propagating eastward and another propagating westward. And these pair of waves are known as the Poincare waves or inertial gravity waves. And that is, we'll sort of discuss them little more details. But let us look at another limit where the frequency is the small, is smaller than 1. Smaller than 1 means smaller than the periods are longer than the rotational period. So that for that you can neglect one other term, and what you will have is remaining is that Ks by sigma is equal to 1 plus k square plus n square pi square, and therefore sigma is minus Ks divided by this term. So these are low frequency waves. So these are high frequency waves, whereas these are low frequency waves. High frequency waves, we have a pair of them, one propagating eastward, another propagating westward. But low frequency wave, I have only one, which is propagating one set of waves, which only propagates westward. And that wave is very much dependent on this parameter S. You remember what is S? S is critically depends on this Coriolis parameter, gradient of the Coriolis parameter. So this the variation of the Coriolis parameter is very is very important for the existence of these low frequency waves. These low frequency waves then are known as Rossby waves. So, and they have several of them are possible for different n. This n essentially represents a sort of meridional wave number. Because the different the wavelength, the meridional wavelength will change for different ends, and so therefore it can be considered like a meridional wave number. So this is a low frequency wave, which it's very much dependent on its existence depends on the variation of the Coriolis parameter, and these are, you can see sigma by k is the phase speed is s divided by this, and that is of course a function of k. So they are dispersive waves, and these waves are known as the Rossby waves. So we'll discuss a little more about them. So you can see that this there are different characteristics of this. We can study from here. What is the kind of, so you can see that these waves at k is equal to 0 will be, the frequency is very k is equal to 0 is at very long wavelength, the frequency will be very small, right? At very high wave very high wave number, that means very short wavelength, this will go as case 1 over k, and therefore that will again asymptotically decrease to 0. So therefore somewhere in between there has to be a maximum, and that maximum can be calculated, and it is found to be k is equal to 1 plus n square pi square. So therefore sigma m, this is the maximum. Somewhere in between, at very long wavelength, the frequency is very small, nearly 0, and somewhere it becomes a minimum, and then again becomes asymptotically goes to 0. And that maximum for a wave number m, it produces a maximum frequency. And but there is another mode, another possibility which we did not discuss, because there is a wave known as Kelvin wave, for which the meridional velocity is identically 0. But since we have derived an equation only for the meridional velocity, then I could not have identified these Kelvin waves. So what we can do is we can go back and put the basic equations. We put meridional velocity equal to 0, and you can derive these two equations. One and from that you can find out a dispersion relation for the Kelvin waves, and this dispersion relation gives me two possibilities. One, a eastward propagating Kelvin wave, sigma by k is equal to, and it is a constant, it is non-dispersive. So these waves are non-dispersive. Sigma by k is equal to C0. If there is one wave that can propagate to the east, and there is another that can propagate. Now I can actually now then go back and calculate what is the amplitude function of this wave. And if we do that, you can go through a solution of those equations and find out. And it turns out that the amplitude function will look like is something like this. So it represents that the y function, it is a wave that will require a boundary, because if the eastward propagating wave can have its amplitude, maximum amplitude to the right of it, where there is a boundary, and beyond that the amplitude will decrease. And the other way, the westward propagating must have another boundary to its right, so that it will have maximum amplitude to the boundary, but then the amplitude has to decrease with the other way. If amplitude of these waves cannot increase away from the boundary, because there is no nothing to support that. So therefore, these two essentially represents a pair of coastally trapped Kelvin waves. So in the extratropics, there is no free Kelvin wave. There are only coastal trapped Kelvin waves. So these waves can then I'll skip this a little bit, little more details about the amplitude functions and those. So these can be now in summary. The Poincare waves have these dispersion relation. The Rossby waves have this dispersion relation, which is westward propagating. These are eastward and westward propagating. Kelvin wave can be eastward and westward. They are coastally trapped, and these waves can be then actually. Then we can also calculate the group velocity of the Rossby waves. The group velocity of the Rossby waves is given by the derivative of these, and it turns out that the group velocity of the Rossby waves is for very long Rossby waves. For very long Rossby waves, the group velocity and the phase velocities are almost close to each other. Very long, but not for the others. So this is important. For most of the planetary scale Rossby waves are very long Rossby waves, and for them the group velocity and the phase velocities are close to each other. That is also an important characteristics. So let me show this in a figure where I can plot all these dispersion diagram, and then we'll stop here.
We'll stop soon. It will be nice.
Yeah, I will stop here. Right now I'll stop, and then we'll have some questions.
Thank you.
So this is a summary of all the waves. So this is here we are assuming that the wave number is positive, and you can have frequency positive or negative to give you eastward propagating or westward propagating waves, and you can plot. So these pairs, these curves are essentially for our inertial gravity waves or Poincare waves, and for eastward and westward propagating, and these are our Rossby waves, and this is where there is a maximum, you see, and therefore this gradient of this on this side of the Rossby wave curve is one side it is negative and this side it is positive. So which means that the group velocity of the Rossby waves for high wave number or the short Rossby waves can be positive, eastward propagating. On the other hand, the long Rossby waves, group velocity is also westward propagating. So phase velocity of the Rossby waves are always westward propagating, but the group velocity can be eastward or westward propagating. So this is also an important thing that we to remember. So let me stop here. These are important, and these two are Kelvin waves. Kelvin waves are here. I'm showing my dotted curve because they are not free Kelvin waves. They are sort of the coastally trapped Kelvin waves. Okay, let me stop here and let us have some questions, and then we'll go over to the equatorial waves. Okay.
Okay. So I think Professor Sandeep can go ahead and ask the question.
Okay.
Meanwhile, yeah.
Okay, thank you. Once again, thank you, Professor Goswami, for a beautiful set of lectures. And I must apologize for very remedial questions. So when you wrote, thank you. When you wrote these equations, I think they were numbered 7, 8, and 9, etc. If I understood, you were neglecting viscosity, for example. Is that right?
Absolutely, absolutely. I have neglected everything. No forcing dissipation. These are all free, completely free. Free normal modes.
I see.
So
and there is some, yeah, sorry, please.
Yeah.
And just to understand, there's some dimensional analysis one can do to say why that can be neglected and so on from the Stokes
basically that is not necessarily we are doing on dimensional. Basically what we are looking at is what are the kind of what are the normal modes that are possible. It is not necessary to whether they will exist, whatever they in reality, obviously the dissipation will modify them. But what exists, like a pendulum has its own normal mode. I am just trying to find out what is the normal mode of the system.
Okay.
That's all. So therefore, the question of the dissipation or forcing is not there right now.
I see.
So therefore, I want to see, and suppose I don't have anything. This system is there. The atmosphere has a layer of fluid. I perturb it. I give I throw a stone, for example, like on a pond. Now the pond will give me what are the possible normal modes or the waves that it allows. And that's exactly what I'm looking at here. So I'm trying to find out what the system will allow. What eventually will happen will depend on how much dissipation is there. What is the structure will be modified by dissipation, which I'll come back to when I talk about the force motion. When I talk about the force motion, then these normal modes will give me the basis of the perturbed structure, and that perturbed structure will be modified by dissipation and forcing. Forcing will generate some of these, dissipation will modify it in some sense.
I see. I got it. Thank you. And then I won't take up too much time, but just in terms of connecting it with your previous lecture, just in 2 sentences. So you had told us that, you had these cells which were formed where the warm air was rising from above the equator and then, going to the poles and then coming back along the surface, if I remember. And will all these waves be important for that process? Just so I have...
Yes, and no. Yes, because I'll tell you. So these are the waves that is possible in the system. And now, so these Rossby waves, this is dispersion curve of the Rossby waves, are the waves that will be allowed by the system. Now, what happens is that in those we also referred to Rossby waves in that lecture, right? Those Rossby waves are these Rossby waves. Some of these Rossby waves become unstable due to drawing energy from the system, the shear of the flow, and therefore, and one of them on particular scale becomes the most unstable, and that is what we see in the weather disturbances. So it is very much related to it, but then it has only a particular one way which has become unstable, and a particular scale is preferred So therefore, that particular scale you see in the weather system, and that particular scale then affects the transports and so on and so forth, and that affects our climate. So there is a connection from these waves to our weather and to the climate.
I see. I see. Thank you very, very much.
Thank you. Thank you. Okay, next.
So next is D. Narasimha. You can go ahead and ask the question.
Professor Goswami, are you
Yes.
able to hear me? My
Yeah,
internet is unstable.
No, no, you are quite clearly.
Okay, you have already. Okay, you have already answered in a sense through your 60 question in equations 16 and 17. The question was about the definition of wavelengths. So for a shallow wave without thermal structure, the question is that your 16 and 17 tell you what exactly the wavelength you mean. More question I want to ask only after you mention any thermal structure, because if there is no other velocity, no thermal structure, what you said is perfect. But the three-dimensional structure, once there is a thermal thing, I think I will wait for you to speak anything. Then I will ask those questions.
Okay, okay, sure.
That is your wavelength part. You have already explained for shallow, that is medium waves, through your equation 16 and 17. That one y square term kills it, but you know how exactly you managed. So that defines your wavelength for these waves. But the question is that the moment there is a thermal structure, instead of your GH, you can have, if the medium has a thermal structure, the forcing term can be due to the expansion of the medium. A hotter medium will have lower density, but then the thing is, yes, of now, I am not asking you that question because you have not introduced any thermal structure.
Right.
So that's all I have.
Thermal structure is there in between, inbuilt in some way. The pi is your potential is related to the temperature. Basically, through gas law and hydrostatics, it is essentially related to the thermal structure of the atmosphere also. So, but I have simplified that in this is just to make it sort of very simple. So when I introduce a stratification, which I am not able to do here in this class, but if I introduce stratification, then I have to explicitly add the temperature or the potential temperature, and that will be your what you are probably saying that.
And it is more than that, because your system need not be adiabatic anymore. Because of that, there are more questions too. But since you are not discussing it, I do not want to divert from your main point. Because the moment you put that thermal structure, it is no longer adiabatic too.
No, right now, exactly. Right now, I am only talking about adiabatic motions right now. So basically, these are all natural normal.
Yes, so that's why I am not asking you right now. I have already told you only after you put the thermal structure. In case needed, I will bring back.
Correct. The second,
okay, that's all I have.
Second lecture, I will introduce forcing, and therefore maybe some this question we can revisit again.
Okay, if you are going to anyhow answer it at that time, I won't ask you. Thank you.
Thank you. Okay.
Thank you. Next is Devabrat Sharma.
Hello, sir.
Yeah.
Sir, in the diagram of the dispersion relation, so is that diagram is for a particular variation of S? Like in S, we have a Coriolis term and that beta term, right? So is it this diagram of different ends of the dispersion relation is for a particular variation of S?
No. S is constant of the system, so, as long as we have a length scale, right? See, S is essentially beta 0 is constant, F0 is constant, L is a length scale which is constant. So this is a constant. So there is only one parameter for right now. So therefore, that value it is all for that for this set of extratropical, I have an extratropical channel where I have F0 is fixed. For that, the gradient of the Coriolis parameter is fixed, and therefore length scale is fixed by these, and therefore this gives me one value of this S0. For this system, I have one value of S0. So that
so it is basically along one latitudinal direction, like along a one latitudinal level, because the Coriolis effect keeps on changing from like equator to pole. So
correct. But this S0, S does not have to change with latitude, right? It is fixed there.
okay.
It does not change with latitude. So we have made this non-dimensional form here. Okay. Any other question, or we'll move?
Yeah. So another question is by Gaurav Chopra.
Good evening, sir.
Okay.
So actually, I was curious about how that del P by del T term came in the continuity equation. But actually, I was looking at like as a Navier-Stokes equation. But then I realized it is shallow water.
Right.
So I'll just go through the derivation of shallow water and find out.
Yeah. I think that will be nice. Okay. Yeah, I see Professor V.B. Rao.
Yeah. So I've asked Aditi to ask question. Aditi, you can ask, and then we'll come to V.B. Rao.
Yeah. BNJ, am I audible to you?
Yeah, Aditi, go ahead.
Actually, there was a statement you made while discussing these modes that Kelvin waves cannot be seen in the subtropical region. So in the subtropical region, Kelvin waves are basically trapped to the coast, which are coastal Kelvin waves.
Right.
So in terms of these derivations, how can we figure out, a particular condition which, sort of does not allow these Kelvin waves, free Kelvin waves to exist outside of the tropical region? Is there a point where we get that, or is that a sort of a limitation of the fluid we consider in terms of the atmosphere or the ocean, if we are talking about it?
No, it is like it is basically a limitation of the extratropical beta plane channel that I talk about. So we are looking at a channel. Channel means that there is a boundary condition, that there is no normal flow in north and south. So this no normal flow has to be satisfied. And by satisfying this no normal flow, you cannot have a Kelvin wave which will have a free Kelvin wave there. It can only have these waves. Otherwise, that Kelvin wave will be unbounded. It will have a very large energy, but you cannot have energy unbounded Kelvin wave, right? So that solution is not allowed, because it cannot satisfy the boundary condition. A free Kelvin wave cannot satisfy a boundary condition. So, when I discussed equatorial case, there I saw that it is different, because the equatorial wave guide itself acts like a wave guide and produces, it allows the Kelvin wave to be confined within the equator. So without a physical, even without a physical boundary, it allows the Kelvin waves to be, because it automatically becomes evanescent from the equator.
Okay. Yeah. Oh, thank you. And if I'm not mistaken, you have not covered the mixed Rossby gravity waves or the gravity waves, right? That is yet to.
Right. Now I am still with the extratropical system.
Okay, I'll reserve my questions related to that for later. So thank you so much, Benji.
Okay.
Professor V.B. Rao, please go ahead and ask the question. I think he's not able to unmute.
His mic is still muted.
Yeah. So maybe if he is still there,
we can come back to him
after half an hour.
Okay. Let us do that. Okay. So let me start again. Then thank you. So let me go to now the equatorial counterpart. So we have discussed briefly. Unfortunately, I think we are packing up a little more than we could in this talk. Okay, let's go back to now equatorial case. Now, suppose I have a channel now around the equator, not in the extratropics. Now, there at equator, your Coriolis parameter is 0. So therefore, f is only beta 0 into y. So that beta 0 is the gradient of the Coriolis parameter at the equator. So what do I expect it to happen? So an interesting thing that is in the extratropical system is that the Poincare waves and the Rossby waves are very well separated in the frequency domain. You see that there the largest Rossby wave is and the largest of these inertial gravity waves are very well separated, and this can be seen from their equations. So maximum sigma max is given the gravest Rossby wave is this value, and dimensionally it is related to beta 0 c0 into f0. And so what happens as f0 goes on decreasing, then this sigma max might also increase. That means as you go towards equator, the maximum of the Rossby wave must go down, and the minimum of these and this is proportional to maximum of the Poincare waves is proportional to f0. So as f0 goes down, this will also become small, and therefore so what will happen is that this maximum, as you go closer and closer to the equator, these will come down and these will also go up. Therefore, the difference between the maximum of the Rossby waves and the minimum of the inertial gravity will decrease. That will make it more difficult to distinguish between sort of separate the Rossby waves and the in the tropics. And this is actually very important in terms of the atmospheric the initialization or problem on the weather prediction, because here now these inertial gravity waves in the initial data is a serious problem for weather prediction. Now in the extratropics, it is possible to separate them in the initial state by doing a normal mode kind of initialization, and that helps to improve the initial conditions in the extratropics. But in the tropics, it becomes more and more muddy and more problematic, and that is something that we'll see at the end of this. So to study the by the way, the tropicals, the normal modes, this is a classic paper by Matsuno published in 1966. He actually derived all the equatorial normal modes from the first principle, just like what I did. And that is most of the material is similar to that. I have just simplified a little. So in the equatorial beta plane, now equations of motions are very similar, but now I don't have a f0 term here in the equation. So it is a beta y into v and beta y u. I'm sorry, one of these is plus. This one is plus, I think. Yeah, I'm sorry, this is a mistake here. So and the rest of the things are very similar. Now here now we have a time scale, and the length scale is from dimensional analysis. I have a velocity scale, and from that velocity scale, and I have a beta parameter, which has a time scale involved in it because the derivative of the Coriolis parameter. So time scale is there, and the length scale is there. From this combination of time scale and length scale, I can velocity scale, I can get a length scale. Now that the time scale now becomes in terms of beta and C0, it can be written in this form. So with these time scale and length scale, I can non-dimensionalize the equations, and these equations will become exactly like the extratropical equation, but without that one term. So once we had eliminate these again, we look for wave solutions, and once we look for wave solutions, and these are the amplitude functions, functions of y, and once I have eliminated these, and I get an equation in meridional velocity, which is like this, where there is no one that non-dimensional number one was not is missing from there. So this is finally our dispersion, this basic equation for V, which is very strongly dependent on the coefficient of V term. Is again looks like a wave equation, but it's not a wave equation because it's coefficient of V is a very strong dependence of Y, the meridional. So as a result, but these are something that we know that this kind of equations are there in the it's very similar to what is known as the Hermite polynomial or equations, and so if we can assume that this term is this coefficient is an integer number, twice n plus 1, then it has a solution which will allow boundary conditions to be satisfied at v equal to 0 at y plus minus infinity, and it will have a solution of in terms of the Hermite polynomials and an exponential function. And this is the main difference, because so we cannot have now simple wave sinusoidal solutions, but the solutions have to be in the form of some of these orthogonal functions like the Hermite polynomials, and that is the major difference between the tropical systems and equatorial and the extratropical systems. And so now the constraint comes from this. So if if this term, this constant is, this is a y square, so twice n minus 1 minus y square, if that is the coefficient of V, then this equation satisfies this solution. This is known in the it's pretty well established from various different ways. People have established that by doing perturbation analysis and so on and so forth. So that so therefore, but that is an assumption that this has to be as an integer twice n plus 1, and so if that is satisfied, then I have a solution of this V solution of this type, and these V solutions are exponentially decreasing, and therefore they automatically satisfy the boundary conditions also. So this is now my dispersion relation. So now I have a dispersion relation for the equatorial waves in this form. Now this is a little more complex than what we did in these in the extratropical systems, and here we have before going further, just let us have some idea about the structure of this now. In the extratropical systems, we had sinusoidal functions, so it was just a simple sinusoidal structure. Now it is Hermite polynomial. So, and this have n equal to different numbers, different for different n Hermite polynomials. Our values are different. So these Hermite polynomials have their own values. With that, these functions with the exponentials can be called size, or they have their own structure. You should remember this, because finally the structure of the equatorial waves will depend on these functions. And these functions have certain characteristics. One important characteristic is that these zero and these even functions are symmetric about equator. This is like a Gaussian function, right? Exponentially decreasing from symmetric about equator, exponentially decreasing from away from the equator. Then we have the psi1 is that exponential function into 2y. 2y means that it is antisymmetric about equator. Positive, negative will have different values. So it will have, so these functions, exponential and Hermite functions together are, when their even functions are symmetric about equator, odd functions are antisymmetric about equator. So this is also an important characteristic, and we have to remember that for future. So now let us look at what kind of high frequency and the low frequency, just like we did in the extra topics, what are their structures, and I mean these the characteristics of these waves. So in the high frequency, now we have a similar kind of a pair of inertial gravity waves, or where sigma square is equal to twice n plus 1 plus k square, and therefore sigma is equal to plus minus of this, and therefore sigma by k1 is eastward propagating and another is westward propagating. So both of these waves are dispersive waves. They are functions of k, and this phase velocity is functions of k, and therefore dispersive, and they're similar to what we have seen in the extra tropics. But low frequency waves are also similar. There is a low frequency limit. I have a Rossby wave, very similar to that in the extra tropics. Somewhat slightly different in terms of these numbers, but it's more or less similar. So this sigma is equal to that. Beta has now been put into normalization, so therefore no beta factor is coming here explicitly, but sigma by k is equal to 1 over k square plus twice n plus 1. So phase velocity is negative, and it has all the similar properties like we have seen in the extratropical Rossby waves. But in addition to that, there is an additional mode here where for n is equal to 0, the dispersion relation is given by this. Now, this dispersion relation can have two solutions, and one solution is sigma by k is equal to sigma by k is equal to -1, and another solution is this. And this, the first one represents a westward propagating Kelvin wave. But if I take this westward propagating Kelvin wave and look at and go back and find out its amplitude function solution, and it turns out that the westward propagating Kelvin wave will be unbounded. As a result, this wave actually will reject. So this particular solution will give me one mode. And what is that mode? That mode is known as mixed Rossby gravity waves. Why it is called mixed Rossby gravity wave? Because these two, it has two solutions for sigma, and if you plot that solutions, so on one side of it has that solution. Actually, I can go and plot that solution here. So if that solution is plotted here on one side, that solution will give me a westward propagating wave, which at small wave number goes to similar to these Rossby waves, and for higher and for k equal to 0, it becomes 1, and then for positive wave number, it becomes increases, and with like a Kelvin wave, it increases with wave number and becomes like very high frequency waves at high wave number. But on the westward propagating side, it tends to become like Rossby waves towards the end of the higher wave number domain. So this is why it is known as mixed Rossby gravity wave. So this is something that is not it does not exist in extratropics. So this is a new mode that is found in the tropics. So there is another new mode that is possible in the tropics, which is given by n equal to -1. But this n equal to -1 is something, is a sort of an arbitrary. But you can go back and say that Kelvin wave. Let us look for Kelvin wave solution. When put that v is equal to the meridional velocity is equal to 0, and then if you look at the solutions, we will find out dispersion relation, which will give me it's a Kelvin wave, which is a sigma is equal to k. So it is an eastward propagating Kelvin wave, and that eastward propagating Kelvin wave is possible in this system, and it doesn't violate any boundary condition. And that is what is a new thing that is possible in the equatorial system. So in the equatorial system, we have a new set of waves. One is, of course, we have the same set of this way. By the way, I have plotted it in a slightly different way here in this. Instead of this is equivalent, but you can always plot. Assume that when frequency is positive, and assume wave number to be positive or negative, so that positive the eastward and westward propagating waves will be on positive and negative side of wave number, and then your inertia gravity waves will now join to each other like this. This is the eastward propagating inertia gravity wave, westward propagating inertia for different n. These are the meridional wave numbers. And of course, we have this mixed Rosby gravity wave which spans. Now these waves are all possible. Now, so anywhere in between, see, this is a space that was not there was no wave was possible in this space in the extratropics. But now this wave is possible. So we cannot separate these Rosby waves from these inertial gravity waves from in the equatorial system. So and that is a major difference between the tropics and the extratropics, and this has an influence. This is an effect on our prediction and so on. And this, of course, the Kelvin wave is the possibility of a eastward propagating Kelvin wave is very important, and this is now this is also new because that is not possible in the for example, in the open ocean, for example, not Pacific, you cannot have a free Kelvin wave going from across the basin, but only coastal Kelvin waves. But in the equatorial Pacific, whole big basin, there is this free Kelvin wave can go. Similar in the atmosphere as well. Atmosphere in the upper atmosphere in the equatorial region will have a Kelvin wave that will go. It will produce weather disturbances and all that. But that kind of thing cannot happen in the extratropics. So these are the major differences in terms of the normal modes that are possible and how they can affect the weather in tropics and extratropics. So how are these waves observed in the atmosphere? In fact, this is a very interesting and important study by, once we have these satellite data. This is a study by Wheeler and Kilades in 1999, I think. So what they did is they looked at, okay, we have these satellites which are measuring now clouds. Using outgoing long wave radiation. Outgoing long wave radiation gives me the height of the clouds, and this height of the clouds, the variations of the outgoing long wave radiation will tell me how the clouds are deeper or smaller or shorter and so on and so forth. So these variations of the cloud height is essentially indicates the variations of the upward motion and the downward motion in the atmosphere, and that is essentially can capture all the variability in the because now we have a daily covering the whole tropical belt. You have a lot of satellites which cover every day all this data for now many years. So they took all that data and did basically separated the simple analysis they did by doing identify a sort of do a double Fourier transform. So you do you find out what are the energy in the different wave numbers in a given day so all the data around the globe you find out a Fourier transform. So in a given day, so you'll get a different wave numbers energy in different wave numbers. Now then you do another Fourier transform in the time domain on each of these wave numbers. Then you will find what are the frequencies that have what is the power in different frequencies. So then you have this this wave number frequency sort of spectra energy in the powers in this wave number frequency domain. So you have this whole wave number frequency from this VLR data for many years, the daily data during summer and winter they separately did and then looked at. They removed the sort of normalized them with the red noise background, and when they did, they actually can see these wave spectra, all these waves very nicely. And this is, I think, it's a very very powerful way of showing that these waves are there in the atmosphere, and these are the only places or wave numbers and frequency where they are excited in the atmosphere. So then they also symmetric and antisymmetric part they separated so that the mixed Rossby gravity waves is seen here, and the Kelvin wave is seen here, and these Rossby waves are seen here. And there's some signals in the mixed Rossby, the inertial gravity waves, but because of their high frequency, no clear signal can be seen there in these. But the large scale, you are seeing these signals very nicely, and that is a very remarkable result, and shows how these waves are there. And this fits so well with this the theoretically, which was predicted in way back in 60s, and now we can actually show that of course there is certain some details that I can discuss in the next class, but the fact is that these waves are now can be seen. But something in this doing that, they found something else which is not predicted by these waves, and this is what is called, somewhere here there is a eastward propagating power at very low frequencies, wave number 2, wave number 1, 2, at periodicity of about 40 days. This was not predicted by our dry waves. So it turns out that this analysis and that is what is today we know as what is called Madden-Julian oscillation. So this Madden-Julian oscillation is a convectively coupled wave which requires moisture. Without that, it does not exist. It cannot exist. It is through the moisture feedback only it is produced, and therefore this is also an interesting way in that even if this particular kind of methodology can actually show us and something that probably was not predicted by the linear theory that of these waves. So with that, let me now so going backwards now, we can actually calculate from those basic equations. As I said, once we know this dispersion relation, I can actually go back and solve for different amplitude functions for the V. Now, what is the structure of these waves in terms of the V and U and the wind in the zonal wind component and the geopotential height? So all these we can calculate. These are the structure functions for their amplitude. Now let us see what is the structure associated with the mixed Rossby gravity wave and Kelvin wave. These are two something very important functions, because those are going to be used in many of our applications later on. And so we must have a good idea about what is the structure. And what is the structure? Because the mixed Rossby gravity wave, if we go back and look at that structure, it turns out that very meridional velocity is symmetric about equator for the that is goes proportional to psi 0, that zero function. And the u and u0 and phi 0 are the geopotential height. The zonal wind and the geopotential height are antisymmetric about equator. So these functions have and there, of course, v velocities are of course in quadrature with u velocities, but u and phi are in phase with each other, but antisymmetric. So these are something that we can get from those equations, and this is important to remember. For Kelvin waves, on the other hand, v is 0, but the u's and phi's are u and phi, the zonal winds and the meridional winds are both symmetric about equator, and this is important. So with these, I can look at what is the structure of u wind and v wind, and then and we'll come back to that in the next class. These structures will be very important in trying to understand the force motion, and some of the other things that are important to note is that there is certain important relationship between these Kelvin waves and the Rossby waves. So Kelvin waves is square propagating, and sigma by k is equal to 1, non-dispersive, but sigma by k is equal to is Rossby waves is 1 over k square into ds. But now for very long waves, suppose towards this end, somewhere here close to many of these somewhere here in this region, close to 0, that's very long Rossby waves and long Kelvin waves. Kelvin waves sigma by k remains 1, but Rossby waves the sigma by k becomes 1 over very small Kelvin k square becomes small, so this becomes 1 over 3. N is equal to 1, that is the gravest, so it becomes 1 over 3. So the gravest Rossby waves, very long Rossby waves, is about 1/3, 3 times slower than the Kelvin waves at that wavelength. So Kelvin waves can propagate, suppose in 3 months, the tropics. The Rossby waves will take 9 months to travel the Pacific. So something like that. This is also going to be important in our. So with that, we can actually have different structures for each of these the Rossby waves and eastward propagating mixed Rossby gravity waves, westward propagating mixed Rossby gravity waves, and Kelvin waves. Kelvin wave is symmetric, and these structures are something that we'll have to keep in our back of our mind to understand some of the force motion. So these actually have lot of applications in this real life, from lot of interpretation of some of the data that we see from satellites in the ocean. We can see that this is a picture of Rossby wave traveling westward from the eastern boundary, reflection from eastern boundary at different. This is sea level height picture from Tropics Poseidon, and sea level height anomalies seem to propagate southward. So some Rossby wave has been generated in the eastern Pacific, and they propagate to the western Pacific in the form of Rossby waves, and that you can calculate what is the phase speed and so on. And you can also calculate the Kelvin wave that propagates. to the east, along the equator, and so on. So some of these things are very much applicable to real life problem. So let me stop here, and then we will discuss little more on. So some of these things that so let me make it. Some of these are all different types of Rossby waves that have emanated from the Eastern Pacific and then reflected back. And one thing that you can see from here, this is another the Rossby wave envelope that has you can see here. So there is a Kelvin wave that propagates to the east and then gets reflected as towards the polar region as Kelvin as coastal Kelvin waves. And while moving towards pole, they trigger Rossby wave response, and that Rossby wave then propagate eastward, westward as Rossby waves. But the Rossby wave speed, as we go higher and higher, the phase speed decreases as 1/y square, and as a result, their phase speed decreases at higher latitude. So therefore, this whole Rossby wave packet that seems to travel has an envelope of this type, that they're slower at higher latitude, and which is reflected in these observations. We have not shown that it is because we have not done that in a sort of spherical geometry. If you do this, we can show that that the Rossby wave space speed, as you go further away from these equator, their phase speed and the group speed will decrease with latitude, and that is again can be seen from some of the satellite data in observations. So with that, I'll stop here today.